This bird may be standing on a wire carrying thousands of volts, yet it looks completely untouched. But one wing reaching a second conductor can turn that harmless perch into a fatal circuit. The bird is not immune, and the wire is not secretly switched off. The answer is a measurement you cannot see, the voltage difference across its body. Both feet usually touch one short piece of the same conductor. With almost no difference between them, the current has no useful route through the bird. Voltage is never just a property of one isolated place. It describes electric potential between 2 points, whether we name both or quietly use ground as the reference. A power conductor can be thousands of volts above ground, so the difference from that wire to the earth can be enormous and dangerous. Move the comparison from wire to ground to one bird foot versus the other, only centimeters away on the same wire, and the number collapses. The bird can rise to nearly the same electric potential as the wire, while the difference across its chest remains extremely small. Even on alternating current, both contact points rise and fall together so quickly that neither foot becomes a useful low-potential exit. That is the first reversal. A frightening voltage relative to the ground does not automatically mean a frightening voltage through every object nearby. The U.S. Energy Information Administration describes the basic requirement plainly. Electric current needs a complete path, an electrical circuit, before it can keep flowing. So whenever someone says a wire carries 10,000 volts, the careful question is not only how high, but 10,000 volts between which 2 points. Now picture the bird as a second path placed in parallel with the tiny length of metal between its feet. Both paths share almost the same small voltage difference. The metal segment has extremely low resistance compared with flesh, so almost all of the line current continues through the conductor instead of detouring through the bird. People often say electricity takes the path of least resistance. More precisely, current divides among every available path according to voltage and impedance. Ohm's law gives the useful intuition. If the potential difference across the body is tiny, the current through that body remains tiny even though the whole wire sits at high potential. A real conductor is not perfectly resistance-free, so there can be a minute voltage drop along it. But across a bird's short stance, that drop is normally negligible. After landing, the bird and the contacted wire behave almost like one electric island, high relative to ground, but nearly level from one foot to the other. The crucial missing connection is an exit toward ground or another phase. Without it, there is no sustained body current large enough to injure the bird. So the bird survives not because of a biological superpower, but because its small geometry usually gives electricity no meaningful voltage difference across the body. The protection disappears the instant a wing, foot, or beak touches a second energized conductor at a different potential while the first contact remains. Now the bird itself completes the circuit. The voltage difference can drive substantial current through tissue, including the chest, in a fraction of a second. A second conductor is not required. Touching one energized part and one grounded bracket, crossarm, pole fitting, or grounded wire can produce the same dangerous path. Large raptors face greater risk because a wide wingspan or long body can reach components that remain safely separated for a sparrow. The dangerous moment may be takeoff or landing, when wings open, feet shift, and the bird briefly occupies far more space than it did while perched. Wet feathers and damp nesting material can make accidental connections more conductive. Dry feathers help, but they are not the main reason ordinary single-wire perching is safe. Sticks, wire, or other nest material may span energized and grounded components, creating a route neither the bird nor the utility intended. Birds also collide with power lines, especially when visibility is poor. Collision and electrocution are separate hazards, even when they occur on the same infrastructure. The pattern is consistent. One compact contact on one conductor is often survivable. Bridging two meaningfully different potentials is what changes the outcome. That is why the familiar row of comm birds does not prove every pole, every wire, or every species is safe under every condition. The U.S. Fish and Wildlife Service identifies distribution poles as a recurring danger because energized and grounded components may be close enough for a bird to bridge. High-voltage transmission structures often separate conductors by much larger distances. The voltage is higher, but the geometry may make simultaneous contact less likely. A bird resting midway along a single conductor faces a different arrangement from one standing on a pole top, surrounded by phases, insulators, metal braces, and ground paths. In open habitat, poles are attractive hunting and resting platforms. That convenience places eagles, hawks, owls, and other large birds near the most complicated hardware. Large groups can make lines sway, and crowded takeoffs put many wings near neighboring parts. A safe static picture can become a different electrical geometry in motion. Wind moves feathers, wings, lines, and nesting material. Electrical risk depends on the smallest separation reached during movement, not only the calm distance in a photograph. Many overhead conductors are bare. A dark surface or weathered coating should never be treated as proof that a line is insulated and safe to touch. Voltage matters, but spacing, grounding, bird size, weather, movement, and the exact perch combine to determine whether a circuit can close. The first engineering defense is separation. Place different phases and grounded components far enough apart that the target birds cannot touch both at once. Where enough spacing is impossible, utilities can cover exposed energized hardware or relocate equipment, so a wing cannot create an electrical bridge. Current U.S. Eagle rules define avian-safe pole geometry using separation between phases and ground, including distances based on an eagle's reach across its body. The cited federal definition uses 150 centimeters horizontally and 100 centimeters vertically for eagles, unless exposed conducting parts are properly covered and maintained. Older hazardous poles can be retrofitted with covers, extended crossarms, relocated jumpers, or safer perch arrangements. The goal is to remove the possible circuit before a bird arrives. Line markers may reduce collisions in high-risk locations, while electrocution fixes focus on spacing and insulation. One structure can require both kinds of mitigation. These changes protect wildlife, but they also protect electrical reliability because an electrocution can trip equipment, damage hardware, and interrupt service. None of this makes touching a power line safe for a person. Humans are larger, reach farther, and are usually connected to ground through ladders, structures, vehicles, or the earth. A hand on an energized conductor, while any other part of the body reaches a lower potential object, can place a dangerous voltage across the chest. Metal ladders, raised truck beds, cranes, antennas, and long tools can reach a line before the person holding them realizes a circuit is about to form. At sufficiently high voltage, an arc can cross an air gap. Copying the exact posture of a bird would not reproduce the bird's size, spacing, or isolation. OSHA tells workers to assume overhead lines are energized, and under common-sighted conditions, keep unqualified people and conductive objects at least 10 feet away. If a line is down, sagging, damaged, or close to work, keep away and contact the utility or emergency services. Do not test it with an object. The physics is the same for birds and people. The difference is the network of contacts each body can make, and humans usually have many more paths to ground. The bird never defeats 10,000 volts. It simply keeps almost all of its body at one potential, so almost no driving voltage appears from foot to foot. Add a second wire, a grounded bracket, or wet material that reaches another component, and the hidden voltage difference suddenly moves across the bird. So the next time you see birds resting above a road, do not ask how they survive a huge voltage. Ask where that voltage difference actually exists. A row of small birds on one clean span is not a miracle. It is a visible diagram of potential difference, current paths, and geometry. The limit is not a single voltage printed on a sign. It is the instant an ordinary body connects two places electricity can use. Subscribe to Ordinary Limits for more hidden thresholds where familiar objects change behavior, and the real answer begins with one detail most people overlook.